Now let's continue directly from the result we obtained on the previous page. We showed that the expectation value of velocity can be written as shown here. In practice, it is customary to work with linear momentum rather than velocity itself. So if we now multiply both sides by the mass m, we obtain the expectation value of linear momentum as shown in this expression. Now let's write down the expectation value of linear momentum in a more suggestive way. We move minus I h bar into the integral, then the bracketed quantity, which is minus I h bar partial over partial x, is sandwiched between psi star and psi. This is exactly the same way we rewrote the expectation value of position in operator form as shown here, where the position operator is sandwiched between psi star and psi. So the bracketed quantity is the operator representing linear momentum. Therefore, it is called linear momentum operator or momentum operator in the position representation. When the linear momentum operator acts on the wave function psi, it produces minus I h bar partial psi over partial x. So we are not merely inventing the momentum operator by guesswork. It emerged naturally from the requirement that the expectation value of momentum, which classically is the mass of an object times velocity, should be consistent with the time evolution of the expectation value of position. So this operator is not arbitrary. It is motivated by the structure of Schrödinger's equation and the statistical interpretation of the wave function. From the integral forms of the expectation values of position and momentum, we see that to obtain the expectation value of any observable, for example, position, momentum, kinetic energy in quantum mechanics, we sandwich the corresponding operator between psi star and psi and integrate over space. Now that we have the linear momentum operator, we can move on to another important observable, which is kinetic energy. In classical mechanics, the kinetic energy is written as shown here. This is very useful because it expresses kinetic energy in terms of momentum. So we have p squared divided by 2m, where p is the linear momentum and m is the mass of an object. Since we already know the quantum mechanical operator for momentum, we can use that result to construct the operator for kinetic energy. In one dimension, the momentum operator is given right here, minus I h bar times partial over partial x. So if we replace p in the classical formula T equals p squared divided by 2m by the corresponding operator in quantum mechanics, we obtain the expression shown here. So this is the standard one-dimensional kinetic energy operator. We then write the expectation value of kinetic energy in the familiar operator sandwiched form shown here. So once again, the expectation value of the observable is obtained by placing the corresponding operator between psi star and psi and integrating over all space. Now recall the one-dimensional time-dependent Schrödinger equation shown here. If we compare this equation with the kinetic energy operator we just derived, we immediately recognize that the first term on the left-hand side is precisely the action of the kinetic energy operator on the wave function. So the first term in Schrödinger's equation represents the kinetic energy of the particle. This is a very satisfying result because it shows that the abstract operator formalism matches the physical interpretation of the equation. Moreover, let me also highlight a broader point stated on this slide. All classical dynamical variables can be expressed in terms of position and linear momentum. This is a very important principle. Once we know how to represent position and momentum in quantum mechanics, we can construct operators for many other observables by translating their classical expressions into operator form. So the key message of this page is the kinetic energy operator can be written as shown here, and this operator is precisely the kinetic energy part of the Schrödinger's equation. Now we are ready to write the general expectation value formula. Suppose A of R and P is a classical dynamical variable. In quantum mechanics, we associate it with a corresponding operator, A hat. Then the expectation value of that observable in the state psi of R and T is given by this expression, where the operator of a classical dynamical variable A hat is sandwiched between the complex conjugate of the wave function psi and the wave function psi itself. This is the general rule. It is one of the central formulas of quantum mechanics. It tells us how to compute the average value of any observable once we know the wave function and the corresponding operator. You can see that the position expectation value, the momentum expectation value, and the kinetic energy expectation value we have discussed are all cases of this one general formula. So the pattern of calculating or computing the expectation value of a classical dynamical variable in quantum mechanics is now clear. We identified the classical dynamical variable, write down its corresponding quantum mechanical operator, insert that operator between psi star and psi, and integrate over all space. That is the basic computational rule for expectation values in quantum mechanics. Now we also need to make an important statement about stationary states. If the wave function has the form of a stationary state, as shown here, then for any operator A hat that is time independent, the expectation value is also time independent, as shown in this expression. The proof is very simple, since if the operator A hat is time independent, then the time dependent exponential factors simply cancel out. We are left with the final result here, which contains no time variable at all. Therefore, the expectation value is constant in time. This is a very important result. It means that in a stationary state, the expectation value of any time-independent observable doesn't change with time. The wave function itself still contains a time-dependent phase factor, but that phase factor drops out of the expectation value. That is why stationary states are so useful and so fundamental in quantum mechanics. They give us stable, time-independent averages for time-independent observables. So these ideas complete an important part of the operator formalism. Once an observable is associated with an operator, its measurable average is computed through this expectation value rule.